Okay, we are live. Hello, everyone. This is Postgres TV Open Talks series, and my name is Nikolai, and my co-host is Ilya. Hi, Ilya.
Hi, everyone.
We are live. Hello, I need to mute myself. Sorry about that. This series is about presenting talks again, which were not recorded at some conferences. And today we have a very interesting topic related to query optimization. And our guest today is Richard Yen. Hello, Richard.
Hi, nice to meet you guys.
Thank you for coming.
Thank you for coming, Richard.
Yeah, Richard works at Enterprise DB, maybe the biggest Postgres company, right? Right, and you already presented this talk a couple of times, and it was not recorded yet, so we have all rights to do it again with recording this time, right? Because right, because good talks should be recorded and available to wide audience. This is our small mission we try to achieve, and it's interesting that I saw your slides briefly, and I have some points where I strongly agree, but I have only some questions. As usual, I remind everyone to, first of all, thank you those who joined us online. This is very important. You can ask questions in chat. We will be monitoring. Only few people do it. Most people watch recording. Also good. Also feel free to ask questions and comments. And I will, as usual, we don't limit you anyhow. Rough rule is like 1 hour, but it's very soft limit, so feel free to speed up or slow down as you want. And as we agreed, we co-hosts have permission to interrupt you and ask questions, right? And do some discussions.
We are your audience, to be your audience.
Right, with small audience.
It's a bit vivid. Some people don't like online talks because it's not vivid. We'll try to do it with it.
Good. Yeah, you can totally grill me and
yeah.
Okay, let's do it.
Let's go.
All right.
Let's share screen and
Okay, so
yeah, I can see it. Good.
Great. Yeah, thanks for inviting me to give this talk online, and I'm really excited to be here. I'll be talking about explain plans, like Nikolai has mentioned. Just real quick about myself, I am a support engineer at Enterprise DB. I've been working there for the past 7 or so years. Previously worked as a DBA, and then before that I was a web developer, and that's how I got started in using Postgres. This is back in Postgres 7.4. We were using making a web app, and it was backed with Postgres as a data store. So as a support engineer over the past 7 years, I've come across a lot of customers who I think the most common question is why is this query slower, or what's causing this query to be slow? And what I find surprising is that many of them don't really know about one of these most important features of Postgres, which is the explain feature. So it's a very powerful tool for developers and DBAs to kind of get a live look at what's going on when the query runs. So that way you can kind of figure out where all the bottlenecks are. So just in terms of this presentation, we're going to just talk about first, what does explain do? And then after that, we'll figure out how explain works under the hood a little bit. And then after that, we'll try to look at some real explain plans and try to interpret the output and understand what are the components of a query execution. And then finally, I'm going to go through some non-trivial real-world examples of how you can use explain to help you debug or improve the performance on your applications. Okay, so for starting off, like, what does explain do? Explain, it tells what Postgres plans to do for a query. So if you type the word explain and then select star from whatever table, it'll tell you what the query planner plans to do. Now, if you actually run explain analyze, it'll actually run the query, and then it'll give you a bit of information about what happened as the query was executed. So this is actually very, very powerful. And we'll get into that a bit more after that. So what doesn't explain do? I think it's important to point out that explain has a just to make sure we don't get confused. There's a lot of things that explain doesn't do. It won't explain why the query planner made a choice. It also won't tell you about query performance being affected by other sessions. So if you have a web app or some kind of application that has many users using at the same time and causing contention on disk, explain won't tell you that kind of stuff. It only tells you for that one query that you ran and what happened. Okay. It also won't tell you about stuff that's happening outside of the database. So like, let's say you have an antivirus software running or some other process, and that's causing your query to be slow because it's causing contention on disk. Explain won't tell you that kind of stuff because it's outside of Postgres. And finally, it won't tell you about external environmental things like network latency. Like if you have, if you're running a query on a remote server and it takes a long time to get that data to your laptop, explain won't tell you that kind of stuff. So just to make that clear for everybody. So we'll move on to the second part of the talk. Go ahead.
Can I interrupt? These are very good items, good points. And like, I also have the same in my mind all the time. And it's like, do you think the lack of this information is something that can be improved by Postgres itself or some tooling additional to Postgres? For example, first item, why some choices, maybe even not why some choice was made, but maybe we should have should be able to see like additional options, like alternative plans, like second best or several plans which lost in competition, right? But also were considered, or for example, affected by another session. If some wait time is included, we will see timing increased in explain analyze, right? But we don't understand why. It was not because of some work was done, but we were blocked by other query, right? Mm-hmm. So we could provide, if we can imagine some tooling which relies on explain analyze, but also checks, for example, persistent statements wait events, persistent static activity wait events, right? Mm-hmm. And it says, okay, like 90% of time spent were done in like just waiting on lock to acquire a lock. So
that'd be a great feature in the future. Yeah,
you agree, right? So like this is something to improve and develop here, right? Maybe inside Postgres or outside.
Yeah.
Mm-hmm. All items are great. I probably will steal them to some places. Good items.
Mm-hmm. Okay. All right. Yeah. So moving on to the next part of our talk, which is basically how does the query planner work? So the way that the query planner makes choices is based on costs. So everything that you have to do in making the query happen incurs a cost. So like the amount of time it takes to pull stuff off a disk, the amount of time for a CPU to make one cycle for a row of a table, there's some costs involved. And that cost is it's a little bit arbitrary, but we can configure to tell the query planner, consider this more expensive than the other thing. So I'll get into that a little bit more in a minute. The query planner also uses table and index statistics, and that stuff is stored whenever you run an analyze on the system. So it's stored in a table called PG statistic. It's basically a histogram of various items that get pulled from a table and stored in this table. And it's a bit, it's not very human readable, so I usually don't encourage people to look there. There are some bits of that histogram that can be interpreted in this view called PG stats. And if you really want to get into that, you can kind of poke your head in that table or that view and kind of figure out what are the statistics for the particular table you're looking for. Like I mentioned, it's refreshed with the analyze command. So whenever you analyze a table or analyze a database, it gathers all the rows and it tries to run some statistics on it, and then puts all that stuff into this table. Don't confuse that with explain analyze. So earlier I showed you explain analyze runs the query. That explain analyze is a very different thing from this analyze command. And then finally, like I mentioned earlier, the costs and stuff are tuned by the configuration. So you can tell Postgres to favor these kinds of joins or these kinds of scans, and also consider certain actions more costly than others. Just to give you kind of a quick overview of what the available costs are, you can see this is pretty much a listing of all the different costs that you can tune. And you can see also like join and scan methods. You can enable or disable those. And as you can see, it's a little bit intimidating for someone who might be new to Postgres to look at these. So generally, I would just focus on these two, random page cost and sequential page cost. And this is basically, random page cost is the amount of cost it takes to do a random seek on disk. So like, let's say you read the index and then you find out the address for a particular row, you have to make a random seek onto disk to pull the actual data off. So that's a random page cost. And the sequential page cost is basically pulling pages off of disk in sequential order, which is basically a sequential scan or a table scan. So we'll kind of go through that a little bit in the following slides. You guys have any questions from here or any comments?
Not yet.
Okay, all right.
I have usual comment that it's already time for random page cost to be almost like sequential page cost by default, because I think most systems already have SSD disks and so on, right?
Right.
Default is not good.
Yeah, I think a lot of it is a bit legacy from the spindle-based disk days, but now most disks are SSD, so maybe we might need to revisit the defaults on those.
Yeah. But you could be probably surprised how many people still sometimes use old mechanical disk, especially in enterprise world. So
I see.
Something with sound, yeah.
Yeah,
and I agree that many databases are on magnetic disks still, but when you stop new database, I think chances are much higher that you will have SSD, and defaults matter for new databases, not for already like installed databases, right?
Another good question is actually if you have some sort of, not like local SSDs, but some cloud provisioned disks. They could be also quite slow compared to local SSDs.
It depends, right? Okay.
Yeah. Okay. Yeah, especially if we're moving to people who are doing like cloud computing, like AWS, they're going to be using SSDs. So they're still used for magnetic disks, and I still have a few in my garage, so might need to keep those around. Yeah, so I guess moving on to our like kind of explaining what how does explain work. So here's just a quick example. I use pgbench to spin up a database, and then I run explain select star from pgbench accounts, and I join that with pgbench branches, and then here's the query plan that comes out. If you notice, so you see that it will do, usually what you want to do is, I mean, some people like to read bottom up and other people like to read top down, but I'm going to start bottom up in this situation. So you have two tables. You have pgbench accounts and pgbench branches, and then you can see that the query planner is going to do a sequential scan on both of those tables. And the amount of cost to scan both of those tables is 2890 for pgbench accounts and 1.01 for pgbench branches. And you may wonder why there are two numbers for the 0.00. So you can see that the first number on the left, which is 0.00, that's the cost that it takes to get to the first row. Now, if you're doing a sequential scan, then basically you just go to that first row and you're there. So you don't have to do any processing to get there, and you can start reading. And then the second number, 2890, is the cost that it gets to have the full table scan to finish. And the pgbench branches table is significantly smaller than the pgbench accounts table, which is why the sequential page cost, sequential scan cost is a lot lower. And then after those scans are done, they're going to be joined using what's called a nested loop. So for every row in one table, it'll scan through the other table set. This is all in memory, and then it'll join together to get one return data set. Okay. So you might be wondering, like, where do these costs come from? So 2890, like, what does that number represent? So what we'll do is in this slide, we're going to hold that thought. Okay, we're going to basically calculate the cost on our own. Okay, so the way that cost is measured is by looking at the sequential page cost times the number of blocks that are sequentially scanned, and then the CPU tuple cost and times the number of rows that are returned, and then times plus the CPU filter cost times the number of rows that were that need to be examined for filtering, right? Because we're filtering by AID is less than 100,000. Okay, so if you look at all these numbers, it's a little intimidating. So we know that the pgbench accounts table is roughly 13 megabytes. Okay, and then you know that traditionally speaking, the block size on a disk is 8 kilobytes. Okay, and you know that if you do the math, relation size divided by the block size, you're going to get 1640 blocks. Okay, and then we know that we're searching on 100 AIDs less than 100,000, so we know 100,000 rows. And then when we look at the defaults in the postgresql.conf, we see that sequential page cost is 1, CPU tuple cost is 0.01, CPU filter cost is 0.0025. Okay, and you plug that all in, and you get to see that the calculated cost for that sequential scan it matches with what we see in the explain output. Okay.
Like it's very interesting. In my past, I didn't understand that and didn't realize until we started to build some tools for query optimization. First thing is, like, hardware is not involved at all anyhow, so it doesn't matter on which hardware we're running it, right? So Postgres just takes statistics and parameters, right? And that's it. It's good to understand, because it means that we can repeat the same on different hardware, right?
Mm-hmm.
And second, also, these blocks, number of blocks and records, they are taken from statistics as well, right? But not from PG statistic. It's from rel pages or like from where? It's also it's maintained by AutoVacuum, I guess, updated by AutoVacuum, right?
Mm-hmm. Mm-hmm.
These numbers, and it also means that is it true that if our table is bloated, it can affect the plan? Like, can bloat affect the planner behavior?
Yes, I believe so. Yeah, you can actually, when tables bloated, the actual size on disk is greater. So you actually have more blocks. Yeah, and that'll basically raise the cost of the sequential scan.
Yeah, this is interesting, because I also didn't realize it until some point that, like, bloat is not something that it's not information, right? It's no number of rows, it's nothing, but it can affect the planner behavior, definitely. Yeah, thank you. Again, it's not more like comments, not questions, sorry. But it's interesting observation based on your example.
Mm-hmm.
Yeah, thank you.
Yeah. Okay. Moving on. So now this is just a query plan. It's not the query execution. So this time I'm going to run explain analyze and the same exact query. Now, as you can see, this time around, we have the same plan, which is nested loop, join filter, 2 sequential scans, but there's some extra stuff that we see. And we see actual times and the number of rows that get pulled out. and it also gives you a little summary at the end, which is the planning and execution time of the query. So let's see. So I guess I wanted to point out how these actual times are the most useful for most of our customers, because they want to find out, hey, why did this query take so long? And as you can see here, we can see that the sequential scan took 25.752 milliseconds, which isn't that much. But if you look at it, if you look at a pretty complex query and you can see, oh, it's this scan or this join that took the longest time. And if you look at the sorry, I think, yeah, so yeah, you can, it's like some people are asking, why is it 56.582 and the execution time was 61? I think generally speaking, there's a little bit of overhead with the OS, with CPU, so that's a wall clock time. So I think there might be some kind of activity going on under the hood that's not recorded. That's why it doesn't always add up perfectly. Okay. Now this is great. I mean, you can actually make use of this and figure out what's where the slow part of the query is, and then try to focus on, hey, this table I need to add an index, or I need to maybe vacuum this other table which is being slow. There's actually a few other parameters that you can pass in besides just analyze. So explain analyze isn't the only thing you can do. There's other things like buffers. You can do verbose and timing. You can actually have it output in JSON and stuff like that. So I'm going to let people go to the documentation for that to find out what all that stuff does. But in this example, I'm going to talk about buffers. So explain buffers analyze.
We actually have a question in the chat.
Oh, okay.
Yeah, I think my comment triggered this question.
Yeah, exactly. But that's what we want. So CPU filter cost and tuple cost are the values dependent on CPU types. If we upgrade the CPU, are they gonna change? That's a nice question, actually.
Yeah. So I guess I haven't seen too much research done in this realm, but like I said, it is kind of arbitrary. You as the DBA or as the owner or person responsible of that server, you can say, hey, I know this thing is like fast. It's like fast like a Ferrari, right? And I'm gonna lower the CPU tuple cost because I know that it can crank through rows and rows of data really quickly. So you can tune that down. The default is what 0.01.
So you're saying that DBA is responsible to change it, because automatically it won't change. This is the problem, actually, right? Because it's like it's quite simple and it does know your hardware, and unfortunately, like we all change random page cost to 1 or 1.1 if we have SSD. This is the common knowledge. Everyone does it. RDS does it by default. But if we switch from slow CPU to much better CPU, do we change it? I would forget about it, actually. And Postgres doesn't do it automatically, and this is a problem, right?
Yeah. Well, so that is I mean, I would encourage somebody out there who wants to do the benchmarking and try to figure out what's the optimal CPU tuple cost to use. That'd be great. But as far as I've worked with customers, we haven't really touched those CPU values because it is a bit risky. Like you're basically affecting all queries, and there's a potential of, hey, I'm a little over eager in tuning it down, and it's going to favor certain like scans and joins instead of other ones. And
it's a big task to check all queries in our workload and see how they will be improved or degrade, right? It's a big task.
Yeah.
It's actually an interesting topic to take a look on those benchmarks of Postgres on M1 processor, because it's like quite different. I think actually if we are speaking about like different Intel processors, all a bit not that outdated processors. So they are quite the same.
Similar.
Quite similar. It's not that much different, I think. Unless we have some crazy workloads like 1,000 workers on for CPU machine, then probably it could have some effect. I don't know actually. It's one of the last parameters we touch as well.
Yeah, maybe never. But some bundles of Postgres have automatic or like suggestion tool for tuning. For example, timescale, they have some kind of some tool, CLI tool, which checks your hardware and offers some settings. I'm not sure if they touch CPU costs, but it's interesting. It's interesting, not very explored area. I mean, for DBAs, right? So
yeah. And I think there's a good reason why people generally haven't tuned to CPU costs. It's mostly because what you're trying to do is you're trying to find a bottleneck, and usually the bottleneck is the disk, right? It's like the fastest SSD is still slower than CPU, slower than the cache. So generally you're tuning the disk-related scan costs, and we haven't really had to say, hey, the CPU should be faster, and try to tune that. So
right, but there
could be reason
some
for that.
edge cases when CPU intensive workloads happen. They happen
Right.
also. But I agree with you. I/O is much more important usually in most cases, but not in all. Right. So good question. Thank you.
Yeah, good question. I like that one. All right. So where was I? I think I was talking about the buffers. Okay, there we go. So so we're looking at buffers analyze, and buffers analyze. What that will do is actually show some of the memory usage that was incurred during the execution of a query. And here we see, so it's the same explain, analyze, output, except there's a couple more lines. So there's buffers, shared hit, and read. So this basically shows us that in the sequential scans, we hit one shared buffer for the pgbench branches scan, and then we hit 2 shared buffers in the pgbench account scan. So basically hit for 2 of those blocks. It was pulled off of the cache, but then the rest of them were read from disk. 1638 buffers were pulled from disk. Okay, so as you can see, this, I think if you have a large enough cache, if you run this again, you might hit more stuff in cache and read off less from disk. Now, I think if you actually do like DML, like if you do explain, analyze buffers on like an update or an insert, you might also see things like, oh, some buffers were dirty or some buffers were written, things like that. Okay. Now, if you have a lot of unexpected readings, so like if you read over and over again 1638 every time you run this, that means it's not getting stored into cache. And what you may need to do is you may need to increase shared buffers so that more stuff can be cached into the into the database. And again, tuning shared buffers is not some trivial thing. It requires a restart, and you need to be careful about using too much memory on your system. So, but at least in some cases, a high read over and over again, that kind of indicates we're not allocating enough memory. Okay, so that so we basically kind of talked about explain, analyze, how it works and stuff. Now let's talk about like the decisions that it has to make. And the building blocks of a query plan involves joins and scans. Okay, and let's look into one more example, okay, with some more rows. So we're going to insert a bunch of rows into pgbench branches, and we're going to run that same query again. Okay, so what we end up with is this time now we have a hash join. Okay, and the reason why is because now there is a larger set of data in pgbench branches, so that a nested loop would not be very efficient. And we'll go into that a little bit more. Okay, you can see that this time it hashed pgbench branches after doing a sequential scan, and then it performed the hash join. Okay. So let's say if I want to force it to do a nested loop. Okay. So keep a note on this one. So with the hash join, the query takes 234 milliseconds. Okay. Now, if I turn off hash join, so I said set enable hash join off, these are all session level parameters, so you don't have to restart or reload the configuration. So I set hash join off and I run the same query again and I force it to do the nested loop. Now, as you can see, the cost is this time around it was 53.89, right? So if you go back, the hash join cost was 48.30, right? So the hash join was cheaper than the nested loop. Okay, so that's why the query planner chose to do the hash join instead of the nested loop. Now that we forced it to do it, we are going to sequential scan pgbench accounts, and then we're going to do a little bit of like index scan on pgbench branches, and then prepare it for the nested loop. So as you can see, the execution time is a bit faster for some reason. I think it's probably because there was stuff that was put in the cache during that first call. Okay, but as you can see, what I'm basically trying to illustrate is that you can force a hash join or nested loop by turning off the enable hash join parameter.
Would be interesting to see buffers numbers here as well, right?
Yeah, it would have been. I guess I can.
Maybe not only timing, but also buffers numbers are better. And just planner is wrong, maybe because we didn't do analyze after our insert. So statistics is outdated, actually. I mean, not all statistics, but right. So interesting.
Yeah. So my example is not perfect. So, but yeah, there are a bunch of.
But they demonstrate a real world example. Like people always like very often forget to run analyze after massive inserts. Common thing.
Yeah. All right. Okay. So now this time around, we're gonna limit to AID less than 100 instead of 100,000. Okay, and what it's going to do, it is deciding to do a merge join, and what that and you can see by doing that, it basically takes two data sets and it zippers them up together. So I'm going to do a little quick overview on joins here. So like we've seen already, the nested loop for each row in the outer table, scan for matching rows in the inner table, which is good for tables where the inner table is very small, right? So for 100,000 rows, scan one row each time. So each of those inner scans are really quick. But if that inner scan is really big, so 100 rows, and then also scan another 100 rows, that's going to quickly get really fast, get really slow really fast. Okay, so the next best join is a merge join. So you basically take the two data sets, sort them all, and then you you line them up next to each other and find the ones that match. Okay, this is good for large tables, and the startup cost is a little bit higher if you have to do a bit of sorting before you do the merge. And then the hash join is pretty much the fastest join that you can do, or the fastest after the hash is created. But basically what you do is you take the table and you build a hash of all the rows, and then you take the one from the other table and you try to find the matching hash. So this is good for equality operations. So you can actually match the hashes pretty quickly. Again, there is a startup cost, right? You have to take time to create the hash, and then you can do the comparison. So high startup cost, fast execution. Okay, so those are the three types of joins that Postgres will do and consider when it creates a query plan. Okay, so like I was showing you earlier, so that the merge and the hash, you have to do like a sort operation too. So that's why it could be potentially slower, but it could also be faster depending on the data size. Okay. All right. Okay, so how can we improve our scanning? Okay, so the scanning, we've seen sequential scans and we've seen index scans. And here's a example on the screen of how an index can make your query go faster. Okay, so basically we have a sequential scan which takes 45.161 milliseconds, and then the same exact query after we create an index that only takes less than a millisecond. So basically what we can illustrate here is that when you index a table or a column, you basically are pre-sorting and you want to find a value that's in the index. So basically BID equals 1, so that's going to probably be at the top of the index. So you hit that and then you go straight to the random page on the disk and then get it back to you, rather than having to scan through the entire table to find until you get BID equals 1. Okay. Let's see. Okay. Now there's a particular scan that's a little bit faster, or it could be a lot faster than an index scan. And here we see that we have this thing called an index scan and index only scan. And what's an index only scan? Well, like I said, right, if you look at the index to do a scan, you scan through the index, find the row that you want, and then pull it off of disk. Now, index only scan doesn't pull anything off disk. It just scans the index, and then you're done. Now, why would that happen? Is because in this example, the top one I did a select star, and then the bottom example I did select AID. Now, if I do a select star, I need to get everything for that matching row, right? The entire row. So I do the index scan, find the row that I want, get it off of disk, and then I can return that to the user. And explain analyze the select AID is I'm scanning the index, and the index is an index of AIDs. So I found the index value with the AID that I wanted, and since I don't need anything else about that row from disk, I don't need to go to disk. I just return the AID that the user asked for. So I only scan only the index, and I just return to that. Now, the reason why I'm bringing this up is because some customers, they I guess out of habit, they just say select star, or they select a bunch of rows, a bunch of columns, and they don't really think about what do I really need to give to my application. And when they put a little bit more thought into that, they discover that, hey, I only need these 2 columns. I don't need, like, all 20 columns. And if those 2 columns are actually composite keys for an index, then they can actually do the index scan and be done. They don't have to get anything off of disk, and that's a lot faster. Okay.
But it can degrade, right? I mean, heap fetches is 0 in this example, and it's a good example. But I saw many cases when, like, you start relying on index-only scan, but then suddenly you see it degraded because heap fetches grow, because the vacuum doesn't keep up properly. So if you want to rely on index-only scan, you need to tune auto vacuum. We have a question in chat. Can you use hints for a query to use specific index?
Yeah, so that's something that Postgres doesn't have a feature for yet. I think people have been asking about that. For the EDB Postgres, we do offer a hints feature. So for those people who are open to using the EDB Postgres, that's a feature that you can leverage to tell it to use a certain index.
Yeah, there's also extension. I think it's even available on RDS PG hint plans, or PG hint plan. I googled it, and not very common, but this extension exists. And the problem is that when you start to use it, you cannot stop, right? So it's one of the questions discussed for decades. Should Postgres have hints? But also, Aurora has some ability to freeze plan. So because sometimes plan flip happens, right? Today we have good index on this scan. Tomorrow it suddenly we switch to some, or today we have hash join. Tomorrow suddenly it's nested loop, and nobody knows why. And it's a problem, right? It's a quite difficult problem to address.
Right.
So,
yeah.
So vanilla Postgres, regular Postgres doesn't have pretty much except additional extensions, and that's right. So,
basically, from my experience,
something with sound. Sorry, yeah, something with sound again. And now it's better.
Now it's better. Okay. So based on my personal experience working with Oracle with hints a lot, it's actually not quite a good idea heavily using hints because workloads have a tendency to change, and you hinted
data
something,
also changing.
Yeah, data changing. You forget to hint. You hinted and forget it. Your data and workload are changed, and well, heavily hinted database, it's prone to administer them. So actually, maybe some things like outlines, they are more progressive in this way than your just pin a plan to a particular query, and then you can search which query are hinted and so on as better. But I doubt actually it's a good idea to implement in community PostgreSQL classical hints like use this index.
But the problem is still there. Sometimes planner is wrong, and our data changed. And for example, auto vacuum is lagging or something, and suddenly plan changed, and due to the planner is making mistake, lagging statistics, for example, plan changed or something, and we have degraded query which is timing out. It happens all the time. So problem exists, and it's hard problem, yes, but like with this should have some tooling to quickly correct without changing application, changing query and so on. We need some tooling anyway. So yeah, it's a difficult problem.
Yeah, I mean, this is why Postgres is always evolving. There's a lot of ways that we can improve the system. Yeah.
Right. Also, maybe a little bit off topic question, but maybe let's answer it right now. Can you help me find out to find out to identify that database is over indexed? I guess that there are indexes which are not.
Oh yeah. So I think that's something we've seen quite a bit. If you look in the pgstat user table, pgstat user indexes tables, those are in the catalog. And you can actually see which indexes have been scanned and which indexes have tuple hits and stuff like that. And for the ones that are very low, you can see that, hey, the query planner is not even considering it, or the queries that you're feeding the database, they don't get planned in a way that would use these indexes. So that actually can hurt your performance, because every time you insert, you have to, or update, you have to update the indexes, and that's extra overhead for your database. So yeah, identifying those indexes that you don't use, that's a very important thing to do.
Yeah, there are scripts around, right, for that. So
yeah.
But what if statistics is fresh, right? Statistics fresh is like it means that the information is not reliable. Ilya actually mentioned some case when index was needed only once per month, for example, on the first day of the month when some reports are generated. And if we look at statistics and it's only 1 week old, for example, and we decide to drop such index, then the first day of next month comes and the report cannot be generated because index is dropped. So it's sometimes tricky. Also, standby nodes, we need to check them as well. Sometimes index is not used on the primary, but it's used on standby. And what else?
You can rewrite those scripts to use them with replica as well. It's like Postgres allows you to check this as well.
You mean, okay, yeah. So you need to gather information from many nodes, and sometimes you have multiple production environments. Extreme case is something like a GitLab, which has GitLab.com, a biggest GitLab installation, and also hundreds of thousands of other GitLab installations. And if you observe only one installation and decide to drop some indexes, others who behave slightly differently may be affected. So there are some interesting cases when you need to understand many things about your.
You can use actually replica foreign data wrapper to figure out those indexes which are used in replica and to monitor with script on your primary. That works
maybe
quite well.
But if you have several production environments, for example, you ship some product to customers and you don't control them anymore. You should be very careful, right? Because one production setup doesn't use some index. It doesn't mean that others don't. So it's quite tricky cases.
Right. Yeah. Always test. Always benchmark. Yeah. Okay. Yeah. So I guess that kind of summarizes the like indexing behavior. One thing I want to point out is that index scan isn't always better. And some of my customers have asked, "Hey, how come I'm getting a sequential scan? I have an index," and there's reasons why, like bloating or index corruption. Those index scans aren't chosen, but sometimes the query planner is making the best choice by using a sequential scan. Now, for example, like let's say you have 10,000 rows that you want to that you have in a table, and you want AID like less than 9,000. So you're going to return 9,000 of those 10,000 rows. You're going to pretty much scan the entire table anyways. So then it makes sense to do a sequential scan, not an index scan. So just for an example like that, the index scan isn't always better. So what I usually tell people is, unless there is a very clear reason to doubt, I would trust the query planner that is making the right choices. That's not to say that the query planner doesn't have any bugs. I mean, you can see PGSQL hackers mailing list. There are some changes that need to happen to the query planner even at this point, but those are usually like pretty edge cases. Okay. This is the last part of my talk is going through some real world examples. Okay, and I think I'm going to quickly go through some of these, but hopefully we'll get through all of them. So this first example is example of bad statistics. Now you can see that when I do an explain analyze, these two, I do it once and then I do an analyze in the second time. And the reason for that slowness, it used to be 24 milliseconds and now it's 3.5. And you can see the rows that it estimates was 35,360, and it actually hit 170 rows. That means there was some kind of bloat, or the vacuum was done and then the analyze was not performed, so that the statistics in the PG statistics table was inaccurate. It's old. So by doing analyze, it updates the statistics, and now it's found it has stored a histogram of 153 rows, which you can see it has chosen a sequential scan, and then it chose an index scan. So by updating the statistics, you can actually help it to choose the best query plan. Okay, so that's why we need to vacuum analyze often and use out of vacuum. Tune that well. That's for another talk. There are some times where you have some situations where the queries, you expect it to use an index, but the query planner doesn't choose to use that index because it doesn't quite know that some rows in the some columns are related. So the classic example is like a cities and states column, right? Like if you select on cities and you join, and then you want to find the ones that kind of have a relationship. Like you as a human know that a city belongs to a state, right? And by doing that, you can kind of filter a little bit. But Postgres doesn't know that. A database engine doesn't know that. It doesn't know that, this is a city and this is a state and they're related. But if you want to convince the query planner that there is a relationship, there's a feature in Postgres called create statistics. And I'm not going to go into that here, but basically you can actually tell it, hey, there's a relationship here, and when you plan for a query, you can use this little bit of information. It's kind of like giving it a hint, but it's not quite the same as an Oracle hint. Okay. Other examples of where explain is useful is by when you can see how this query, it has it does a sort and then it spills off into disk, right? So when I do an select from pgbench history where delta is less than 0 ordered by delta, right? It spills that sort. It spills out to disk, and I had to get 2.6 megabytes on disk in order to perform that sort. And the reason why that it had to do that is because we didn't allocate enough work mem. The work mem was 4 megabytes, and coupled with the other stuff that you have to do to run the query, 4 megabytes is not enough. So let's set it to 16 megabytes. I think there isn't really an exact formula here, but in this example, I decided, hey, I think we're gonna give it 16, and then when you do the query again, you actually get a better performance. Yeah, you had a question?
Actually, yeah, it's more like a comment. I think I agree. Like work mem 4 megabytes is very, very, very outdated default as well.
It's a default. Yeah,
hundreds of gigabytes of RAM. We should increase it. And and this is a perfect example. Like I'm highlighting, costs is different, meaning that here plan didn't change. I mean, structurally, it's also 6scan, so it's the same. But cost change, right, and means that it could change. I mean, the decision, planner could choose different plan because cost changed, right? So interesting, also consideration. Work mem is not a part of planner parameters. If you check PG settings, there are categories for each parameter, and work mem is outside of planner parameters category, but it definitely affects the planner behavior. So it's and I agree it should be increased on most cases. It's very important to make things work properly, right?
Right. Yeah. So that's one of the first things that customers should look at, and they know their system, they know how much memory is on it. Yeah, but maybe we should increase the default, but that's a discussion for the community to decide.
In PostgreSQL Hackers, there is ongoing discussion from Andrei Borodin that he explained it to me recently. There is a problem with PG star statements that when it's quite volatile, it's for a query analysis, right? So to find bad queries, if it's very volatile, so new entries are constantly inserted to PG star statements, and if work mem is very slow, then risks of locking issues on PG star statements are much higher. So it's thing that can hit many Postgres setups and underestimated. So why we don't see it in heavily loaded production systems? Because work mem is already increased. So there is an unexpected risk of low work mem. So work mem should be increased, definitely.
Yeah.
But of course, if memory allows, right? So.
And listeners should remember that work mem is a per session config. So if you are expecting, hundreds of users, you don't want to set work mem globally at the postgresql.conf level. Otherwise, you might run out of memory. You can do it per session. So like in this example, I could just say set work mem equals, 4 gigabytes just for the session. And then I'll have more memory to do that sorting just in that one session that I have. Okay, so then it's a lot less risky than changing postgresql.conf to 1 gigabyte for everybody, and
people do that by the way.
They do, yeah.
Over provisioning, actually.
Yeah, on a 32 gigabyte memory machine, you got 100 users using a gigabyte each, then you're going to run out of memory
it's
very
not
quickly.
allocated immediately. That's why people do it. It's allocated like if we need, it's dynamic allocation, right? So it's not like shared buffers. Session doesn't take this memory immediately. It only uses it, but it can use it multiple times. So things even more and more difficult for proper capacity planning. So each session can use multiple work maps, but not always. So you need to maybe to change it iteratively, right? Observing and so on. It's tricky. There is no good formula here, unfortunately.
Right. Yeah. Okay. Let's see. Okay. Another example of how the explain helps is by looking at the situations where there's index definition mismatch with the queries. So in this example, I have a index I created on substring on the filler column, and I just want the first character. Now, notice how the other queries that I run, I use substring on, lowercase of the filter. I use the first, the first one character of filler with left. It doesn't choose that index just outright. It actually does some bitmap scanning, which is something else I didn't get to talk about in this talk. But you can see that it doesn't use it as you would expect. Now, if you actually call it the exact same way that it was defined, the index was defined, then it will know, hey, I will use this index and it performs a lot better. Now, maybe that is something we need to improve in Postgres to kind of give a little more, I guess, artificial intelligence to say, hey, maybe I can use this index even though the way that it's called is not the same way that it was defined. But yeah, so right now the way that indexes work is really a one-to-one. The way that it's defined needs to be the way that it's called to be able to use it. Okay. Okay, some other situations that I had come across, prepared statements. So if you have a application that uses prepared statements, that's pretty common in Java, and there's some apps that are written in like Python and PHP. They prepare a statement and then they call execute over and over again. Now, the way that Postgres works with prepared statements is the first 5 executions use a custom plan, making a separate plan for each of those executions. But then after that, the 6th call or 6th execute onward, it just creates this generic plan and uses it over and over again. So sometimes I've seen that happen where it uses a index scan for those first 5 times, and then for the 6th time onward, it uses sequential scan because it doesn't have enough information about that, what parameter is going to get passed in as the argument. So it can't reliably say, oh, I know I can use this index. So then it creates that generic plan using a sequential scan instead. Version 12 onward, you can actually change the plan cache mode so that you can say, I will always use a custom plan and never use a generic plan, which is good for some customers because they'll get a custom plan for every time, but it does incur a higher CPU overhead because it has to go through the trouble of generating a new plan every time. Join order, just-in-time JIT compilation. Those times, sometimes those will cause slowness in the query as well, and you'll see that in the explain output. Sometimes our customers have seen situations where they have lots of tables, like 20 tables that they're joining together or using from this is 20 tables, and at a certain point, the query planner it takes a lot of work to figure out the optimal plan. So there's a parameter in postgresql.conf called from collapse limit, join collapse limit. After this number of tables, stop trying to optimize that query plan, and just I guess it doesn't drop those tables, but it doesn't come up with, it doesn't put in the extra effort to come up with a better plan. So you may want to increase that if you have a lot of tables, but when you do that, you will have to remember that there is that extra overhead of generating a optimal query plan. Okay. Finally, ORMs. So a lot of our customers use ORMs, and that does create some unexpected behavior. And here's one example of that. We had a customer where they were saying that their updates took a long time. And when they came to us, they said, hey, you know, this update's taking a long time. We don't know why. And this is the bottleneck for our application. And when we ran it by hand, we could see that it was only 0.252 milliseconds to do the update, but the customer was reporting 40 milliseconds. So that's 400 times slower. And we kind of scratched our heads. I mean, why would that happen? And when we used auto-explain, we discovered that the reason for the slowness was actually because the ORM was converting a numeric value into a double precision. And because, like I said earlier, the index definition mismatch, it could not use a index scan. It had to do a sequential scan on the table. So I guess that's the last thing I wanted to kind of talk about in this talk was auto-explain. So as you can see in this example, auto-explain is actually very useful, right? Because when you as a user run something, the explain only comes out when you say explain whatever, and you at the PSQL terminal get to see that output. But in this customer situation, when they do that by hand, they can't. That's not exactly one-to-one with the application, right? Like I typed in this query, but then when I pass it through the ORM's doing something else, and I don't know what final query ends up at the database. So auto-explain is good for that, because it takes whatever query that it received from an application, and it prints out the plan that was created. And basically, it's something that I think it's included now, so you can actually leverage it. It does create extra I/O on disk, and it does incur a little bit of CPU, so you might want to use it sparingly. But it's very good for situations like this where you're stuck and you don't know how to figure out this issue, and auto-explain does give you that visibility into the system. We also had a recent situation where the auto-explain showed us that environment variable wasn't being passed. So you can actually do stuff like explain nested queries. So like if you do explain on this function call, when you do it by hand, it just says I call the function. But then if you use auto-explain, you actually can print out all the selects, all the inserts, explain plans for all the stuff inside of that query, which is also very useful for debugging. Okay, so I think that's it, all the time we have. So hopefully that was pretty useful for you guys.
I think it's very good tutorial style, like covering many things. It's very hard to talk about explain because so many details, and what to choose for one hour session, it's a big question. So I think I enjoyed it. You raised many important questions. Mm-hmm. So and we had good questions. No more new questions in chat, but thank you everyone who asked questions. Also good discussions. I kept one question for the end. So it's not also maybe not as usual, not a question, but maybe a comment. You mentioned overhead from having an index. So any change will be slowed down a little bit because the index should be maintained. And if we have many unused indexes, it's definitely our inserts, updates, and deletes are slowed down. But there is also one more overhead I only recently realized, and here I want to advertise our in our channel. There is a podcast, Postgres FM podcasts, which we do with Michael Christofidis. We did an episode recently about index maintenance, how to find unused indexes and when to clean them and so on. And I realized the interesting point: even if index is not used at all, not only it slows down your writes, but also it spams your shared buffers and caches, like operational system cache as well, because even if you don't use it, updates need to load pages of index, and it's present in shared buffers. So cache effectiveness also affected, right?
Yep.
So it's an interesting point that, like, if you have a lot of unused indexes, then probably cache effectiveness in terms of hits and reads for shared buffers is also a little bit worse than it could be. So cleaning unused indexes is a good idea as well.
I actually saw even a more horrible landscape than you have lots of objects in your database.
Again with sound, something with sound.
One, two, three. Just and now.
Okay.
Works better.
Better again.
Right. Stupid. Sorry. So I actually saw quite much more stupid situation than you have lots of objects in your schema, like millions of objects, like tables and so on. And some frameworks in this case trying to add like 10 indexes for each table for each case. You end up with many millions of objects, and in that case you can actually hit a problem. Then your PG catalog swaps to the disk, and that's a very funny story. What's going on with your database? But well, that's an extreme in terms of amount of indexes.
Yeah. Sometimes engineer decides to index every column. This is not also a good idea, right? Let's index every column. we use all columns. I paid for all columns. I will use all columns and indexes all columns. Not a good idea. But how do we find holistically which index to choose? Like, what's your approach? How to find proper index set? For example, we have queries. Okay, we have pgstat statements. Do we need to experiment with all queries manually, like? But to run explain and see the plan and decide manually, or there is something like holistic approach, some tooling which will help us automatically find proper indexes?
Yeah, that's a tricky one. I mean, there's no silver bullet there, but I think that's what staging environments are for. So you write an application, you run your tests in staging, and you discover, oh, these are the columns that get used a lot. These are the ones that get a lot of sequential scans, and then we'll create indexes to kind of make that go faster. And I mean, databases are always evolving, right? Your data set's growing, you get bloat, you get partitioning and stuff like that. And I think as you go, you have to kind of regularly and kind of do a little bit of reflection and figure out, hey, do I need more indexes? Can I get rid of this one? And do some testing around that.
Yeah, sorry, I pulled you to my territory. Staging is my territory. Like, how to build proper staging. If, for example, we have 10 terabytes database or 1 terabyte database, but our staging is only 100 gigabytes, it's testing on staging will not be good enough. It will not be representative because plans will be different, right? In arbitrary case, sometimes they will match, but not always, right? So are you saying that we need to build better staging, and this is a big question for query optimization?
Yeah, that is a thing that you have to kind of consider. Some customers have the ability to do a one-to-one staging environment. Like, I have a 10 terabyte database and I'll have a 10 terabyte staging database. Some customers can't do that, and I think that's
because of privacy, right? So personal data and
privacy,
GDPR
costs,
and so on.
Yeah, maintenance and all that. So it is a bit harder to do. you know, in my work as a developer, I mean, we are tasked with that that challenge. Like, hey, you know, try to create as accurate of a environment as what the customers would get. And you know, even stuff like, hey, you know, what is the caching behavior over time? There's no way to know unless you actually have an environment where, you know, you're running for many months at a time. So yeah, I think there isn't a very easy way to answer that question, but
right.
but
A shameless question from me, like even if we can copy like 10 terabytes production, 10 terabytes staging, and we have two engineers that work on optimization. One engineer created index, and another engineer didn't know about it, right? What do you think? This is a problem also, right? How to solve it? Get second staging, or how to solve it, or try to guess. This is big problem actually. Why shameless? Because this is what we do at Postgres AI. We solve this exactly problem. We provide thin clones, and on one machine we run multiple full clones independent, so anyone can experiment. So like, I just wanted to advertise because this is an interesting problem to solve, and I think it's super important. Like where do you experiment? How do you experiment? Super important problem, right? Sorry, I could not bypass this opportunity. Okay, anything else? We want to, for like final questions, final words, or no? If no, thank you so much, Richard. Again, like very good tutorial. I think I will use the link to this video to people who want to start working with explain plans and so on.
Cool.
Great. Thank you so much.
Yeah, it's very happy to be here with you guys.
Thank you. And thank you everyone who watched us online, especially, and everyone who will do it later. Ask questions and comments. We are monitoring them. And as usual, subscribe, like, and share in your working groups, social networks, Slack, Telegram, and so on.